seminar this academic year, this semester. So thank you all for sticking with us, and we'll resume after the summer with a new program, new fresh start. Meanwhile, today we are super happy to have Tommaso Denti. Thank you for accepting our invitation for this talk. The title of the presentation is Understanding Information Acquisition through F-informativity and Duality. This is a joint work with Alex Bloedel, who is also in the audience, I can see, and Luciano Pomatto. We are also super happy to have guest panelists today with us, Weijie, Zhong, and Liang. So the format is the same as always. The talk is 1 hour with questions and comments from the panelists, but if any of you have any other questions or comments, you are also allowed to obviously to unmute yourself and ask questions. Please use the chat. We will filter the discussion in the chat. If there's anything that needs to be mentioned, we are going to let Tommaso know. After 1 hour, we have Q&A session for 15 minutes, and the talk is recorded for that period. After that, we'll stop the recording and say goodbyes. All right, Tommaso, the floor is yours.
Should I share your slide?
Yes, please.
Can you see the slides?
Yes,
but we can see the slides, but we can see the whole desktop.
Okay. That's it.
Okay, that's better. Thank you.
Okay, thanks for coming and for inviting me. We changed the title of the paper since 2 days ago, and probably we'll change it again. But the important thing is this is a paper on information acquisition. And in particular, it's a paper about a model of information acquisition that have become especially popular in recent years, models of flexible information acquisition. So what are the main features of flexible information acquisition? So first of all, the acquisition of information is modeled as the observation of a statistical experiment in the classic style of Blackwell. So specifically, take the perspective of a decision maker, single agent. There is some finite states of nature theta. The decision maker doesn't know what is the true state, and but the decision maker can acquire additional information about the state by running an experiment. So what is an experiment? An experiment P is a collection of probability distributions over a signal space omega. And the probabilities are indexed by this unknown state. So the idea is that the experiment describes the relationship between signal and state. And the stronger the relationship, the more the agent learns by running this experiment and by observing the signal. So a couple of simple examples. So imagine that the state is binary, and the experiment is just tossing a coin. So there are two possible outcomes, heads and tails, and the coin is biased so that if the state is 0, heads is more likely, while if the state is 1, tails is more likely. So in this case, by running this experiment and, for example, observing heads as the outcome, this provides evidence in favor of state 0. Another simple example, again with a binary state and a continuous signal space omega. Now the signal is normally distributed with a mean which depends on the state and a known variance sigma square. So in this case, observing realization of the signal that are close, let's say, to 0, provide evidence that the underlying state is 0. So the key aspect of flexible information acquisition is that the decision maker can choose what experiment to run and has access to virtually any experiment. So you have to imagine a decision maker with a lot of experiments he can choose from, maybe Gaussian, maybe discrete, maybe binary. Conceptually, these models of flexible information acquisition are interesting because they allow us to examine not only the precision of the information, like the overall effort that the decision maker put in acquiring information, but also the type, the quality of the information the agents seek. because of kind of like this richness of the set of feasible experiment, in these models, really kind of like the key parameter is the cost of information, which is described by a functional C over experiments. So this is really kind of like the key objects here, and this is also what this paper is going to be about. Finally, the model is closed by assuming that the decision maker chooses the experiment by balancing the value against the cost of information. So models of flexible information have become quite popular recently with many applications. This is a literature that essentially started with the work of Sims on rational inattention and spawned in many fields. And Weijie, for example, has a kind of like an important paper in this area. Now, virtually all of these papers in this literature, especially in applications, they commit to a specific functional form for the cost of information, which is based on Shannon mutual information. So what is this cost of information looks like? Basically, the cost of running an experiment P is the expected Kullback-Leibler divergence between the signal conditional distribution and the signal unconditional distribution. So here we are using pi to denote the prior overstates, and p subscript pi, the unconditional signal distribution, the ex ante distribution over signals. So the idea here is that basically by looking at some notion of distance between the conditional and the unconditional signal distribution, this is telling us something about how informative the experiment is, because, the more the distribution of the signal depends on the state, the higher the informativeness of the signal. And here, this cost of information is supposed to be increasing in the informativeness of the experiment. So the more information is acquired, the higher the cost. So this cost function really depends on the choice also of this distance between probabilities, and this distance is the Kullback-Leibler divergence. So in economics nowadays, we are quite familiar with this quantity because it shows up in many places, for example, in the literature on misspecification. So here with Kullback-Leibler divergence, the distance between two probability distributions depend basically on their log likelihood ratio. Is their expected log likelihood ratio. The idea is that the more variability there is in this log likelihood ratio, the higher the distance between these probabilities, and so the farther away they are. And finally, there is just a scaling factor kappa, which kind of like parameterizes the unit cost of information. So these functional form have been extremely useful in applications, and has been really kind of like paved the way for this type of models. The key advantage of this specification is really in its tractability, because when you take this Shannon mutual information and then you look at what is kind of like the solution of this information acquisition problem, the behavior, the resulting behavior takes a tractable logit shape. Everybody likes logit, and so this is kind of like the main reasons why this Shannon mutual information is so popular. Of course, there are also kind of like foundational work, but I would say that most of the people use this not because they think that this is the way to model the cost of information, but because of its tractability. Now, this particular specification for the cost of information also comes with important caveats. In particular, it has been kind of like many papers at this point, they have highlighted theoretical and empirical challenges that come from this specification of the cost of information. I'm going to be more precise later on in the talk about what are the limits of this specification with mutual information. But even now, you can imagine, this is just one functional form, and you can imagine that this cannot really capture the heterogeneity and richness of information acquisition problem that agents face. As a response to this problem, there has been a growing literature on developing alternative cost functions with many papers, most of them are very well published. But I think it's fair to say that it is still an open question how to basically move these models of flexible information acquisition beyond mutual information while preserving tractability. So this is key. This is kind of like preserving tractability, we think is very important, especially if we want our models to be used in application. And
Tommaso, is your approach going to nest these alternative costs, or is it going to be something different?
Yes, in the end, we are going to nest this cost. Okay. You'll see more specifically what we're going to do. And so this is where this paper comes about. So we are going to extend this flexible information acquisition beyond SIMS model with really a focus on developing solution methods. So this is not going to be kind of like an axiomatic work in which we put some axioms and then we see what are the cost of information that comes out. We are really focusing on kind of like being able to solve these models. And there are going to be two main innovations. First, we are going to introduce a class of cost based on F divergence, which is a generalization of KL divergence. And answering Annie's question, the class of cost that we are going to propose, they're going to basically generalize the cost that people have looked at, but they're going to do it kind of like in an interesting way. The second innovation is that we are going to develop kind of like novel duality technique to analyze information acquisition problem. And putting together these two innovations, we are going to be able to propose new functional forms. So now functional forms that the literature have not considered before, that address the limitation of SIMS model while maintaining substantial tractability. So for example, we are going to be able to link the resulting behavior to popular generalization of logic, such as nested logic and mixed logic.
Sorry, I just wanted to make sure my question was clear. So I actually meant the third bullet in your last slide. So the alternative cost functions that other people have proposed.
Yeah.
Is your approach going to be nesting those papers as well, or just I'm not too familiar with what these papers had proposed? Are these going to be special cases of what you guys do, or is this some sort of?
Yes,
okay.
They're going to be special cases. Okay. What we are going to see, so we are going to develop solution techniques to solve information acquisition problem for basically all these cost functions, but we're going to go beyond that. Okay.
And I guess one way to explain is that a majority of them are UPS, and Tommaso is going to show us UPS is nested.
Exactly. But what I also want to say that the perspective that we take in this larger class of cost function are going to also suggest new cost functions that people have not considered before. And in fact, in a sense, our proposal is going to be kind of like to look at this new cost function, which we believe they have tractability properties that maybe go beyond what people have considered before. But this is going to become clearer throughout the talk. Okay. So very quick plan of the talk. So first, we're going to do a kind of like a review of what is known about information acquisition under mutual information, because this is the material that we want to generalize. Then I'm going to give the two main definitions for the paper, this notion of F divergence, and then the resulting class of cost that we use, that we build, which we call F information. Our main result is going to be a characterization of information acquisition under F information, this generalization of mutual information, using duality techniques. And finally, I'm going to give you an overview of the applications, so where we put these tools into practice. Okay. Are there other kind of like questions about the positioning of the paper? Otherwise, I jump into the model. Let's jump into the model. So first, we're going to do this kind of like a quick review of information acquisition under mutual information. So model, a single agent, uncertainty about the state of nature. There is a finite set of states theta, they distributed according to some prior pi. There is some finite set of action A. The decision maker has to take one of these actions, and the utility that the decision maker obtain from an action depends also on this unknown state. To simplify the exposition, from now on, I'm going to do a normalization. So I'm going to identify basically actions with a subset of R theta. So the idea is that I'm going to identify each actions with the vector of payoffs that they deliver in every state. So A theta in this case is going to be interpreted as the utility from action A in state theta. It's just a normalization. So the decision maker, before deciding what action to take, can acquire additional information about the state. We are going to model the acquisition of information using the language of experiments. So the decision maker chooses an experiment P. Omega is the final set of signal realization, and P theta is the signal conditional distribution given the state theta. We are going to denote by calligraphic key the class of all experiment with finite signal space. We're going to focus on finite signal space because basically it is kind of like basically without loss of generality, given that we look at decision problems where the set of actions is finite. Any other question?
You just answered it.
Yeah, yeah. So I guessed correctly. The cost of information is modeled by a cost function C defined over this class of experiments. Costs are non-negative. They could take infinite values, which they just represent the situation in which some experiments is not feasible. So this is the cost of information. What is the benefit from acquiring information? Well, is the fact that the decision maker can condition the choice of an action on the realized signal. We are going to model this using an action strategy sigma, which just specifies for every signalization omega a distribution over action. Putting everything together, we obtain a kind of like the object that we are interested in, an information acquisition problem. So the decision maker chooses an experiment and an action strategy to maximize expected utility minus the cost of information. Let me just go through very quickly this expected utility calculation so that it is helpful to remember the notation. So a state theta is drawn according to this prior probability pi theta, then conditional on the state being theta, signal omega is drawn according to whatever probability the experiment specifies, then given signalization omega, the decision maker take an action A with the probability specified by this action strategy sigma, and then finally the payoff is realized, which is A of theta is the payoff of action A in state theta. So the decision maker kind of like trades off the value of information, the first part of this objective function, against the cost of information. Now, under the standard assumption that C is increasing in the Blackwell order, which is an assumption that we're going to maintain in the paper. So this cost function is kind of like the more informative the experiment is in the order of Blackwell, the higher the cost. One can immediately simplify a little bit this information acquisition problem by invoking kind of like a sort of version of the revelation principle for these information acquisition problems, in which it is without loss of generality to assume that the signal space is the action space and omitting just the action strategy. So this is truly kind of like a version of the revelation principle in which basically you bypass the mapping from signal to actions, and you interpret signals directly as action recommendation that the decision maker is willing to follow. So given this simplification, then the decision problem is just basically choosing a stochastic choice rule, so a mapping from states into distribution over actions.
Tommaso, can I ask a quick question? I'm not familiar with this stuff too much, so is this sort of revelation principle, the Blackwell order is sufficient? Is it necessary, insufficient? Is there exactly a relationship that we? I mean,
I never tried to prove that result. The Blackwell order is sufficient. My guess is that it's also necessary, but,
okay.
but certainly there is a very close relationship between these two. This is the assumption and the result.
Okay.
Excellent. So as I said, kind of like, so basically the goal of the paper is really to kind of like provide the tools to solve this optimization problem, characterizing the optimal experiment, but also the value function. What we know from the literature is certainly how to solve this problem when the cost function has this specific functional form based on mutual information. And so let me show you basically what is the theorem that everyone uses in applications when they kind of like they assume mutual information and they want to use these tools. So this is going to be a characterization of the optimal choice rule. Okay, it's from Mateka and McKay and Kaplan, Dean, and Lee. So an optimal choice, a choice rule P, a mapping from states into distribution over action, is optimal if and only if there is a distribution alpha over action such that these two conditions are satisfied. So before we look at these two conditions, let's just focus on the first kind of like the statement of the theorem. As you see, kind of like the theorem, the essence is a dimensionality reduction. You go from trying to characterize a mapping from states into distribution over actions to just kind of like studying, analyzing an unconditional distribution over action. Okay, so it's a dimensionality reduction. And so then how do these two objects are linked to each other? This is described by the first condition of this theorem. So the probability at the optimum, the probability of taking action A in state theta basically takes this functional form which really looks like logic. In fact, if for a moment we forget about this object alpha that we are trying to characterize, then the probability of taking action A in state theta is exactly kind of like given by a logit shape in which basically it depends on the relative utility that action A delivers in state theta against what is the utility that in state theta the other feasible actions deliver. Okay, so this is just basically a state-wise version of standard. This standard logit model is modified in this condition by this distribution alpha, which is an endogenous object. And this is basically the difference between this model of stochastic choice that comes out of this mutual information specification of the cost of information and standard logic. And basically, why we need this modification, why we need this kind of like benchmark probability alpha to kind of like weights this logit form. Well, you can see that, for example, something that this distribution alpha is capturing is the role of the prior. So the prior clearly is an important object in the information acquisition problem because it affects the value of information. But if we look at standard logit without this alpha, then only the utilities that these actions deliver in the state matters. This clearly cannot be kind of like, even abstractly right kind of like at the solution of an information acquisition problem. The prior must matter. And so this is one of the things that is distribution alpha is capturing. Okay. The way I think of this is basically, in a sense, a minimal modification of the standard logit model that can be used to study information acquisition. So from this first condition, basically the only objects that really is endogenous that is left to characterize is this distribution alpha. And the second condition of this theorem tells us how to find this distribution alpha. This distribution alpha basically is the solution of an auxiliary maximization problem. Now, I don't want you to focus too much on the exact functional form of this auxiliary maximization problem. If you're familiar with this is basically the surplus function of the logit model with some modifications. The important thing is that this is a kind of like a relatively nice functional form. This optimization problem is concave, so the first order conditions are necessary and sufficient. This is differentiable. The first order condition can be computed analytically in a simple way. And so this is kind of like the sense in which one can study this nice looking optimization problem to characterize this endogenous object alpha. Something to mention is that in general, this optimization problem does not have kind of like an analytic solution, but one can tackle it also with computational techniques, being kind of like concave. Another nice thing is that this auxiliary maximization problem returns the value function of the original optimization problem. So this theorem gives you a characterization both of the optimal stochastic choice rule and the value function. So what is this mysterious object alpha? Well, it turns out that this alpha is exactly the unconditional action distribution. So it has this interpretation. So overall, the theorem basically gives you a way to characterize the stochastic choice rule, the conditional probability of choosing an action given the state, just by focusing on the unconditional action distribution, which is a simpler object. This is kind of like, I really like this result, and many people liked it because really this is why people use this model in applications. And in a sense, in this paper, our goal is to generalize this theorem, and this is what we are going to do. Have this theorem for a more general class of cost functions. So before we do that, I need to tell you what is this class of cost functions that we look at. So F divergence and F information. So the object that we use to define our cost functions are what are called F divergences. So this is basically a generalization of KL divergence. So if you remember, mutual information is defined in terms of like Kullback-Leibler divergence. Our cost function are going to define in terms of a generalization of KL divergence, which is called F divergence. So this is kind of like widely used in statistics. Some of you may already be familiar with these objects. Let me just describe it to you. So the F divergence between P and Q, now P and Q are just two probabilities over signals. What is this divergence? Is basically, again, the expected likelihood ratio, but now instead of having kind of like a log here, we have a function f that weights it. So the idea is very similar to KL divergence. The distance between two probabilities P and Q depends on the variability of the likelihood ratio. The more variable the likelihood ratio, the farther away they are. And to capture this aspect, the important assumption of this function f is convexity, so that variability in the likelihood ratio is kind of like increases this expectation. And then in the slides, there are a few more technical details which are not important. As I said, KL divergence is a special case in which this function f has a specific functional form equal to x log x. Throughout this paper, we are going to actually be interested in a generalization of F divergence because here the F divergence is just measuring the distance between two probabilities, but if you our experiments, they are composed of multiple probabilities. For these reasons, we are gonna be concerned with a generalization of F divergence called multivariate F divergence, which is basically serves the purpose of measuring the distance between a set of probability distributions and a fixed distribution Q. So the multivariate F divergence is exactly a measure of divergence between a set of probability distributions, say P1, Pn, and a fixed probability distribution Q. Ultimately, these P1, Pn are going to be the probability distribution that our experiment is for. Then the idea is kind of like the same. The F divergence between this probability distribution P1, Pn, and Q is just expected likelihood ratio. But now we are kind of like considering all possible likelihood ratios, so that the function f is kind of like multivariate, again convexity, kind of like penalizing the variabilities on this likelihood ratio. So one way to think about this is that basically in the slide before, we were computing the distance between these 2 points. Here, we are computing the distance between a set of points, P1, Pn, and a single point, Q, okay? A special case, of course, is the one in which this function f is additively separable, and so then the distance between these probability distribution P1, Pn with respect to Q is just the sum of the individual distances, okay? But in general, we look at something more broad.
And in that case, that returns the previous case, or?
So if n is equal to 1, we go back to the previous case. It's just the distance between 2 points, P, P1, and Q. Here is a generalization.
Yeah, sorry, I meant the examples at the bottom.
The example of the bottom is basically you can think of it again. Yes, if n is equal to 1, we go back to the previous case, but you can just think of it as a way to construct this kind of like, you know, if you think about here, you're trying to construct the distance between a set and a point. One way to construct a distance between the set and the point is basically by looking at the distance of the single element of the set, and then, for example, averaging them out, which is what we have here. But in general, there could be kind of like, you could drop this separability, and then this is what this multivariate function f allows.
So is mutual information one of those additively separable cases?
Exactly, that's what I'm trying to ask.
So now we are generalizing KL divergence. Now we are going to generalize mutual information in the next slide. Okay, just bear with me one moment. So this is the new cost function for information acquisition that we consider in this paper. So the cost of an experiment P, what is going to be? Is going to be the distance, the minimum distance between the probability distribution that form this experiment and a fixed measure Q. So here, for simplicity, I'm saying the states go from 1 to n. So P1, Pn are the conditional distribution of the experiment. If you take, so we are in this world in which basically this is the experiment and this is a fixed Q. We are measuring the distance between these probabilities and this Q, and then we minimize overall possible Q. And this distance is this multivariate F divergence.
So, Tommaso, can I ask a couple of, just to clarify, because so in the standard stuff, there's two things that are not clear to me. That they may be related, they may not be. The first one is here, the P1, there's one for each state, right? So and Q is fixed. Now, yes. It seems to be the wrong way around, in the sense that what you have is perhaps the prior, which is fixed, and then you're finding the P1 to Pn that minimize the distance. Instead, here you're fixing the let's say the posterior, if you will, in some ways, given by the experiment, and then you vary the prior. This is how I'm interpreting this. Probably is the
let me give you let me give you kind of like a simple way to interpret this cost, and then we go back to this function. Basically, this at first may look a little bit, you know, unusual, but in fact, what we are really trying to do is kind of like generalizing some notion of mean and variance. So now forget about all this business with experiments. Take endpoints on the real line and say that you want to measure how these points are kind of like distance from each other. Ultimately, this is also what we are going to try to do with our experiment, in the sense that the informativity, how informative an experiment is depends on how different these conditional distributions are from each other. And so this is what we are trying to capture here. Let's try to do this exercise simply in a simpler framework, in which we have just endpoints on the real line. We want to see how far away they are from each other, how different they are from each other. A simple way to do it is by compute their variance, okay? They are kind of like the distance of each point, the square distance of each point from their mean. Now, simple calculus kind of like shows that the variance can also be represented as the value of a minimization problem, in which basically instead of computing the distance from the average of this point, you compute the minimum distance from some fixed point y. It turns out that basically in this problem, in this minimization problem, the mean of these endpoints is exactly the minimizer of this objective function, okay? What we are trying to do, the idea behind our cost function is exactly the same. Basically, we can think of f-information as a general, kind of like a measure of the variance of these conditional distributions over signals. How do we compute this variance? We compute it basically according to some generalized notion of mean, which comes out of this optimization problem. In fact, we interpret basically the minimizer of this problem as kind of like a notion of mean of this experiment, a notion of mean that of course kind of like depends on the particular distance that we use here. In the same way that here, if we want to generalize the notion of mean for a set of real numbers, one way to do it is you take this optimization problem, and now instead of using the square distance, use another notion of distance, kind of like, for example, another power, and this is going to give you another notion of mean, and it's going to give you another notion of variance between points, and this is exactly what we're after here. So this is the idea behind. Yeah.
Sorry, finish your sentence.
No, this is the idea behind this cost function.
Can I just talk through something to make sure I'm following?
Yeah.
So if we ignore the inf for a moment,
yeah,
and I compare this with mutual information, can I think of it as mutual information maintains additivity with respect to both theta and also omega? And here you're maintaining additivity still within with omega, but you're not requiring that across theta we're adding up the distances.
This is certainly one of the differences with mutual information, an important one. So mutual information has this additivity across, I mean, I think mutual information has an additivity basically, let me just say, so yes, this is one of the things that we are generalizing. We are dropping the additivity, for example, that we see here, to a more general functional form. And this is, we are going to do it basically because we want to capture situations in which basically distinguishing nearby state is, you know, to basically the additivity with mutual information, something that gives you is that the cost of information is invariant to the relabeling of the state. But there are situations in which the lab, you know, the way that these states are labeled matters. And so this is kind of like one way in which we are generalizing. We are generalizing that.
Tommaso, can I go back to your explanation? I'm going to ask a lower level question than the one Annie asked. So basically here, my intuition is that you kind of know the Q because that's probably going to be the prior, but you don't know what P1 and Pn are. Indeed, the theorem that people use that you showed us before essentially constructs the P1, the P thing, starting from your prior, essentially. So here I'm thinking of a constructive approach. But it seems that the way you define the inf and so on, you're doing it the other way around. And I think your explanation below. So what I guess what you're going to show us later, tell me if I'm wrong, is that this problem is, you can kind of look at the problem in a different way, where you do start with the prior and then you figure out what the P1, Pn, because otherwise it seems hopeless. And this is where the duality, I guess, comes from. Because otherwise it would be hopeless to say, let's pick P1 to Pn at random and see what's the closest Q. How many possible P1s can you see what I mean? It seems.
So I think so. You're probably kind of like I like the way the way you're thinking it. I like it. Maybe let me add something using the next slides, which I think is going to help to kind of like increase the understanding. Let me discuss a couple of special cases. So one special case actually comes from statistics, from the 72 paper by Cisara, which is basically the case in which now kind of like we don't do what Annie was suggesting. So we do what Annie was suggesting in a sense. We assume separability. So now this multivariate F divergence is just kind of like the sum of individual binary distances. Okay, so when we compute the distance between this experiment and this Q, we just compute it state by state, and then we average. Okay, this is the model that, in fact, this paper is the one that gave us the idea to look at this functional form, which otherwise, for the cost of information, which otherwise would not be intuitive at all. And in fact, in a sense, it's the contribution of the paper to propose this functional form. At first, maybe kind of like why you are doing that, and show that is useful for these problems. What Cisara noticed is that mutual information is in fact a special case of this specification. So even if there is this inf operation, mutual information arises as a special case, because if we take KL divergence as our specification of F divergence, then basically we go back to mutual information, because the solution of this minimization problem is exactly the unconditional signal distribution. So much like with mean and variance, in which kind of like you go into this minimization problem and then we end up with the average, here is the same. You go into this minimization problem and then we go back to this unconditional distribution. So this is kind of like a property of mutual information, which Cisara exploited to offer a generalization of it. Okay. In the paper, as I mentioned, to answering, and so maybe answering Francesco, you see here, we are not minimizing respect to the price. So this prior pi is fixed, for example, in this computation of this objective function, but we are minimizing according to this average signal distribution. In a sense, you're kind of like decoupling a bit these two objects. As I mentioned in my answer to Annie, so we go beyond this separable model for two reasons. One, because exactly, we want to model situations in which the cost of information is not invariant to the relabeling of the states. This is going to be important in the application. The other reason is that by going beyond this separable case, we are actually able to cover basically the vast majority of the cost function people have considered in the literature. Now, if you're not, this is
Tommaso.
Yes.
Could you go back?
Yes.
I'm just speculating, but just to answer maybe Annie's and Francesco's question earlier. Here, are you trying to, let's say, use an analogous approach to the rational inattention literature, where Q serves as a purpose of that alpha you introduced earlier? And
that's exactly
P is
right. This is where we are going.
So you turn the problem into like a two-step optimization problem, where now you can do alpha and P separately.
That's exactly right.
And then you are generalizing like the structure while keeping the duality there, right?
That's exactly right. I mean, like, okay, if you're not into this literature, but this is Weijie's intuition is exactly the right one. So the is a technical intuition, but is exactly the right one. And maybe we are going to see it a little bit later in the theory. Okay. This is why this thing works. I was mentioning another thing more maybe from the insiders, even if nowadays this literature is quite popular, so people are kind of like familiar with these terms. So when you think about generalization of mutual information in the literature, the class that people looked at is this class of posterior separable cost. I don't need to go very much into details. It's basically a cost functions in which basically you think of it as the experiment generates posteriors, there is a cost to generate every posteriors, and then you average across this cost. Now, at first, this cost function looks very different from what we are doing. For example, you don't see any minimization problem here. But the point is that by choosing this function f carefully, and in particular by using infinite values for this function f, we are able to actually subsume in our analysis the entirety of this class of cost functions. So going back to kind of like what Annie said at the beginning, we're proposing something new, but then in the end, we are gonna, the tools that we develop, they apply also to this standard case. Okay. Any other question? Otherwise, I move to basically the main theorem of the paper.
Sorry, go ahead.
You can defer the question if that's going to take too much of a time. But if you compare this expression with the mutual information expression on the last page, the mutual information definition actually does not satisfy this property that it explodes to infinity, right?
So what you picked up is that different function f's, different f transformation, different function f, can induce the same cost of information. So in particular, mutual information can be written in this way, okay, within this class, but can also be written in this way. One way to think about it is that, and so this means that, there is not a one-to-one relationship between the cost of information and the function f. This is also an occasion maybe to point out that, in a sense, when people in the literature have tried to generalize mutual information, they've tried to generalize mutual information starting from this slide, looking at this way of writing it. In our paper, this is really, instead, we kind of like, we try to generalize mutual information looking at this alternative representation. So these two representations, one with this minimum operation, the other one with kind of like infinite cost, they deliver the same cost function in a sense. But when you think about the generalization, they suggest different things. Annie, you had another comment?
Yeah, so right, I think it's very interesting that how you guys decoupled Q from P pi, I guess. But I'm just trying to think through how to interpret it, right? Like there's a sense in which this whole entropy-based literature is very prior dependent. And that's in contrast with another literature in which we think about costs of information as objective. And it feels like what you guys are doing is some sort of interesting intermediate case where this is still going to be prior dependent, right? But somehow that Q that you're picking.
This is a very, very good comment. Let me comment on this. So in this paper, this business with the prior is kind of like irrelevant in a sense, in the sense that we take the prior as fixed. So the dependence on the prior does not play any role. Maybe let me. In a sense, for us, it's so here we are specifying this cost with this dependence on the prior, which Annie picked up, because we want to speak to the literature. But in terms of what we do, if you take this prior away and then you specify the cost without the prior, just by summing over states, it's totally fine. It's just another specification for F. So this is a paper that, in a sense, it's agnostic about that issue. I have my opinions about that issue, but here we are agnostic. If you want to put the prior, in fact, we put it exactly because we want to kind of like be able to explain exactly what is the relationship with the standard.
Right, but like, so is there an interpretation for Q? And I think some of the comments in the discussion are also related to this.
It is the way to think about it is that so it is a generalization of the notion of mean.
Yeah, I can see that, but like
maybe one thing. So in terms of the observable objects in the model, in the end, are going to be these unconditional probabilities. So this is the stochastic choice, the thing that if you go in the lab, if you go in the data, this is what you observe for every state distribution of elections. Now, in the case of mutual information, alpha can be easily computed because it's just the average using easily computed if you have all the information. Here, the relationship between alpha or Q and the optimal Q and these unconditional probabilities is a little bit more subtle. So there is not this simple averaging relationship. It's a generalization of that. In the paper, then, for specific instances, we do a good job in giving kind of like an interpretation of this alpha. Basically, there's sort of like some measure of salience, ex-ante salience of these actions. So we do give kind of like behavioral interpretation in specific for specific in specific cases, but that's right. In general, that's what I can say.
Is it too much of a stretch to think of it as like the prior signal distribution for which P1 through Pn would be least surprising?
I've never thought about it in that way, but it sounds really nice. So I'm going to try to, maybe it's a good interpretation. We haven't thought about it, but something in the neighborhood of that. Okay, it's certainly some benchmark probability, some measure of salience of these actions, or what you're suggesting is also very interesting. But I cannot say. I have to think about it to answer it. I hope you're right, because then you can write it in the paper and it's going to look nice. Okay, let me maybe jump into the theorem. I think with 10 minutes I should be able to describe it and then very quickly move to the applications. So then the main theorem of the paper kind of like solve this information acquisition problem with F information. The key idea is going to be kind of like to use some duality techniques. In particular, we are going to study information acquisition so basically in this model, this cost F kind of like it is completely identified by this function F. So you can imagine, okay, I'm going to have to solve this information acquisition problem. It's going to be something about this function F. Yes and no. We are going to see that the solution of this information acquisition problem is going to be about this function F, but only through a transformation of this function F, its conjugate. So let me introduce these objects, which is going to be key for the theorem that we want to prove. So what is the conjugate of a function F? So takes this transformation F that we have been thinking about. Its convex conjugate, F star, is the solution of this optimization problem. So convex conjugate, standard operation in convex analysis. It is a way basically to associate, to map one function into another. So also this function star, F star, is defined on R theta. And in fact, it's an operation that has many examples in economics. Maybe kind of like the most famous example is the conjugacy relationship between cost and profits function in producer theory. Let me use this analogy to give you kind of like an intuition for this optimization problem. Now, again, forget everything about information acquisition. Go back to Mascolel, Wiscon, and Green, chapter 3. Take the perspective of a firm in a competitive environment, choosing how much to produce. Imagine that every theta index one of the goods that the firm is producing. So Y in R theta is basically this plan, this quantity production for every good. Then what is this? Now imagine that interpret F as the cost of producing this vector of quantities Y. What is this first term? Let's think of X as a vector of prices. These prices could be negative, but who cares? Now this is revenue. So this optimization problem is maximizing profits, revenues minus cost. And the value function is the profit function. So in producer theory, this conjugacy relationship links cost and profit functions. In this paper, we are exploiting the same kind of like duality between this function F and its conjugate, okay? The key of this operation is that there is a one-to-one relationship between F and F star, so that basically you can alternatively think of this problem either in terms of F or in terms of F star, and conceptually you're not losing any information. And as you will see in a moment, for us it's going to be important to think of it through F star. So forget about this extra assumption. let me just say that for simplicity, I'm going to assume that this conjugate function f star is differentiable. And I'm going to denote by the gradient of f star is derivative. This differentiability assumption as a kind of like counterpart in terms of the function f. And so here is the main result of the paper. So under f information, a choice rule is optimal if and only if there are a distribution over action alpha and a vector lambda in r theta. You can already think of it as a Lagrange multiplier, such that these two conditions are satisfied. So again, let's first focus on the first part of the paper, or the first part of the theorem. So again, the theorem, the essence of the theorem is a dimensionality reduction. We go to try to characterize a map from states into distribution over action to try to characterize two simpler objects. One, a distribution alpha over action, as in the Mattek and McKay paper, but now we have an additional object that we need to characterize. We are trying to do something way, way more general, so something has to give, something has to give. And so we also need to characterize the additional endogenous object lambda, and it's going to basically, it's a Lagrange multiplier. You can already think of it. So how this stochastic choice rule is linked to these objects? Again, the first condition tells us that. So the probability of choosing action A in state theta is basically this benchmark probability alpha, okay, modified by what? By a term that depends on the derivative, that depends on the derivative of the conjugate function, computed in A, which is basically the entire vector of payoffs that this action A delivers, multiplied by the prior probability over states, subtracted by the Lagrange multiplier lambda. I claim that this expression is a generalization of the logit shape that we saw before, and let me show you why. So we have this form for the conditional probability of choosing action A in state theta, okay? Now, clearly, these probabilities, they have to sum to 1. So without loss of generality, I can normalize this probability of taking action A in state theta by the sum of the probability of taking alternative action B in state theta. This is the expression I end up with, and now we start to see kind of like the resemblance with the logit form, right? So basically, we have this alpha, which in the logit model is this unconditional probability of taking action, multiplied by a term. What is this term? Now let's see what happens with mutual information. With mutual information, basically, this derivative of the conjugate function as a particular functional form, which is exponential. This is just by computing, okay? Now, you plug in this exponential form, and what happens? Well, because of the property of the exponential function, basically, this Lagrange multiplier goes away, and we go back to the standard logit, to the standard logit form for mutual information. So this is, you see, kind of like, this is what we are trying to do. We are trying to kind of like generalize, in a sense, this exponential form. And we are doing exactly that using this conjugate function and its derivative. We are in particularly dropping the kind of like separability of cross states. The price that we pay is that now we need to introduce an additional endogenous object lambda. Notice that this object lambda is not that it's not there with mutual information. This is not 0. This is a Lagrange multiplier. Basically, it's the Lagrange multiplier on the constraint that this probability in every state they sum to 1. So this is not 0. It's positive as some value with mutual information. It's just that because of the properties of the exponential function, it drops out. And in a sense, this shows you kind of like what is the additional tractability that you get with mutual information, which is the fact that basically you kind of like don't need to characterize the Lagrange multiplier to find the stochastic choice rule. This is a property, an additional tractability property of mutual information, but not a specific, not kind of like, there are, as we show in the paper, there are other cost functions that allows you to kind of like characterize this Lagrange multiplier. Just to wrap up, then the second condition is basically kind of like tells us how to find this alpha and lambda. and they are the solution of an auxiliary max minimization problem. So it's kind of like the solution of a zero-sum game. So again, it's the generalization of what we saw before. Before here, we have a maximization problem. Now we have a max-min problem. Again, in general, the solutions of this max-min problem cannot be computed explicitly. But this is a max-min problem. It's a nice structure. It's concave, convex. One can compute analytically the first-order conditions, and they're necessary and sufficient. What I was mentioning before. So what is so if lambda is a Lagrange multiplier, what is alpha? Alpha is the f min of p, is the q that we saw before. I'm out of time. I just want to mention one thing, and then maybe kind of like in the questions I can say something about, in the Q&A I can say something about applications. What is kind of like probably one of the main takeaways of the paper is that now, if we look at this theorem, if you look closely, the function f basically in these two optimality conditions that we need to solve to find this to solve this information acquisition problem, the function f never shows up. It's only the function f star, its conjugate, that plays a role. And this basically suggests that if we want to look for kind of like nice functional form for discourse functions, we should look for nice functional form, not necessarily for the function f, but for its conjugate. And this is basically, in a sense, what distinguished this paper from the literature. In a sense, the literature, they were, most of the proposals in the literature of alternative discourse functions, they've been looking for nice functional form for f, but I think it's fair to say that, anyway, this paper shows that, in a sense, the real object that we need to think about when we think about tractability and property is not f per se, but the function f star. Okay, and this is basically then the perspective that we take in the applications, where we propose specification for a star to generalize mutual information and address its limitations. But let me stop here so that there is a proper time for the Q&A. I have some extra slides for the applications. I'm happy to cover them, but let's do first the questions.
Thank you very much. So this was super clear. Very great talk. Thank you very much. So we are moving to the Q&A session, and typically we start with our panelists, but the audience, please free to join. We have another 15 minutes. Annie, Weijie, do you have any other comments or questions for Tommaso at this stage?
Anyone want to go ahead first, or
I feel like I asked mine during the talk, so yeah, you should go ahead.
All right. Can I actually share my screen?
Oh, excellent. It's
Now
recorded. We are recording, but that's
Okay, so no, I just want to draw something. If not possible, then I'm just describe. I like the figure you draw on the board where there are dots, right? And then basically what we're doing is that each dot is 1p theta, and q is the closest point you want to find according to some variance measure. I think there it's good to draw an analogy to mutual information. Mutual information is basically the version where first, the distance is defined by KL, and second, the different thetas are weighted by prior, and third, they are additively separable. Right, so mutual information can be described as this, f cos with these three features. And I think it's good to derive certain examples where we drop each one of this feature and see what's the implication here. Right? What's the extra generality we get from dropping separability, dropping the prior weight, or dropping the log functional form?
We kind of do that in the applications. So again.
All right, so we run out of time, but yeah.
Okay. The applications, I mean, like in a sense, are where the paper really comes alive. And the applications, they kind of like do that. So we have first applications in which, the prior again is, I don't think is super crucial for this paper, but we have a set of applications in which we maintain the separability and we change only the the exponential function. And there we show that basically you can, this is going to kind of like be something about generalizing the responsiveness to incentives. And where am I? Oh, here. Oh, but now I want to share my screen again.
Yeah, we got it.
So we have a first set of applications in which we maintain this separable form, and instead of having a, in the dual, let's say, instead of having an exponential function, we have other functions. And we look at these to think about the sensitivity to incentives. So, for example, whether whether people kind of like react more to small changes. The sensitivity to incentives. Let me put it this way. And a very interesting thing here is that here, unfortunately, I have a typo in the slide. So think of it as this is F. So this is F. So in the conjugate space, very interesting thing is that in the conjugate space with the mutual information, you have an exponential function. Okay. Because of the properties of duality, basically, you give me any conjugate, there is an underlying cost function. So this means that when you try to kind of like generalize mutual information maintaining this separability, you can choose any function f that is not exponential that needs to maintain kind of like two important properties, which are the properties of these conjugates, which are convexity and monotonicity. So take any convex and monotone function, we can do kind of like, we can generate new cost functions. And it's interesting because in economics, what are the monotone and convex functions we are familiar with? They are the utility function over money. And in fact, this then creates a whole kind of like new set of ideas for us, because now we can use tools from risk theory. Now, I mean, of course, kind of like for us, usually the utility is concave because we are risk averse, but from a technical perspective, if it's convex, it's just risk seeking. But this link between kind of like risk theory and optimal information acquisition in the dual space allows us to basically use the tool of risk theory to analyze mutual information. For example, we see that a very big role to characterize this reaction to incentives is the Arrow-Pratt coefficient of f star of this conjugate function. And in this kind of like spirit, mutual information basically corresponds to a Cara utility function. The whole thing is that, the Arrow-Pratt coefficient of the conjugate function, you will never think of it as an important element to study information acquisition because it's not the first thing that you think about. But once you do this operation, then it becomes rather natural. And then there are our propositions that shows that this is in fact a way, in a sense, to capture the curvature of this information cost, but done in a dual space. So this is kind of like, and then basically, and then kind of like we have another set of application in which we drop the separability, and now we propose kind of like non-separable conjugates to address these kind of like situations in which the structure of the state space is important for information acquisition. For example, where the state space has a natural topology like the real line, and you want to model this issue that distinguishes nearby state should be more difficult than distant ones. Again, I don't want to, let me see if there are other questions.
Excellent, thank you very much. Are there any other questions in the room? There's some action in the chat, but yeah, please go ahead, Enrique.
I have a question. So can you go back to the definition of the DF? So I was wondering if there's some relationship here with the Bregman divergence. Is that Is that a particular case of that?
First, hi, Enrique, nice to see you.
Hi, nice to see you.
So let me see. So in this case, in this bivariate case, I think that there is some result out there that the only F divergence that is also a Bregman divergence is KL. Maybe I think does it, I don't know if it's a result that Weijie and Alex have used in their work, but I think there is a result that I remember that there is some kind of like incompatibility between these two classes. In this general multivariate attribute case, I don't know. I would have to look into that. I'm not 100% sure.
All right, thanks.
Thank you.
Max.
Can I? Yeah, come on, go on.
Hi. Hi, Tommaso. Hi, good to see you.
Hey, come on.
Hey. A quick question. I'm not sure how much relevant that is, but the state space you take as finite, right? And then you show that the topology, is it possible to extend these results to, a continuum of state setting, state space setting?
So, okay. So the tools that we use so the proof of this theorem is actually, I mean, it's okay, but it's not terribly sophisticated in terms of tools. It's basically Lagrange multipliers and then some transformations. So this means that basically the tools that we use are kind of like convex analysis. And so one can imagine that insofar as one can do infinite dimensional convex analysis, which is necessary to deal with kind of like a continuum of state of continuum of action, one can generalize this theorem. Now, of course, already Lagrange multiplier. So these are kind of like delicate, it's not, there are certainly some regularity conditions that one needs to check. And also in general, these rational, anyway, there is a path to generalize these results to a continuum of action, continuum of states. But of course, there could be kind of like non-trivial technical condition regularities that one needs to kind of like check.
Sure. And could I also quickly ask also regarding the CISR 72 result, right? There was this characterization of, and which was related to the mutual information, given also another way of given a different form of representation of the mutual information cost function. So there's this infimum over these Qs, right? So I was wondering, from an economic perspective, is there sort of kind of some justification for this argument operation, like in the sense of your paper with Massimo and Aldo, or Alex's paper with Weijie, right? From this experimental perspective, decision maker like does experiments, and then each experiment costs something, and over time, or Morris and Strack paper along that line. So in that kind of sense, could there be any justification for this infimum operation? Because mathematically, sure, that's a true result, but what is the what is the decision maker doing in terms of coming up with this cost function? So what is the intuition there in terms
It's
of
an interesting question. So I mean, in a sense, the cost functions that we propose here, they are a black box as the cost functions that people use in the literature. So and there has been some work, in particular by Weijie, Alex, and others trying to kind of like open this black box and trying to give kind of like a more structured model, underlying model of information acquisition. We have not So this is basically an open question, I would say, for our cost functions, and also for cost function that people use more, that have been using in the literature. The fact that this mean operation may suggest, as you are suggesting, maybe kind of like a foundation that is different from what people have thought about so far. It's a very interesting perspective. Hopefully someone is going to work on that. We have been working on this paper for so long. The paper is so long, but we are very close to a draft. Hopefully within a month or so we're going to have it.
Yeah, great paper, thanks.
Thank you.
Thanks, Kamal. Any other questions before we finish the official?
I have a question where it's for almost for the not recording phase.
So in that case,
wow.
In that case, let me say
let
me say thank you again, Tommaso, Annie. Weijie had to go, but we thank him again. Alex was very active in the chat. Thank you very much as well. And from us, organizers of VSET, this is the last talk before the summer. So we hope we'll have a great summer, and we hope to see all of you in late September, early November. Thank you very much. I'm going to stop the recording.
Recording stopped.